Welcome back to the deep dive. Today we're getting our hands dirty. We're not talking about abstract market forces or politics. We are diving into hard, practical engineering,
The really hard stuff.
the really hard stuff.
Mm.
Specifically, what it takes to build a complete vehicle testing and verification plan, a DVP&R as they call it, for one of the most complex machines you can imagine, a 400-volt P2 hybrid cement mixer truck.
It might sound, a bit niche, but the engineering challenge here is just monumental.
Huh.
Taking a high voltage system that loves clean, stable environments, and you're dropping it into a machine that lives in constant.
It's got to be the most hostile environment for an EV system, maybe outside of what, deep space?
I'd say so.
Yeah.
Mistakes.
Yeah.
They are absolutely zero tolerance. We talk a lot about functional safety in cars, preventing injury.
Right.
But here, the risk is also just massive capital loss.
Right. If that mixer drum stops turning because the electric motor, the ePTO fails, the concrete inside starts to harden?
That's the nightmare scenario, the canned concrete risk. It can literally mean scrapping the entire vehicle. The chassis just becomes one giant, useless block of concrete.
So the huge engineering report we're digging into today, it really frames this whole process as like an engineering exam syllabus, a brutal one.
It is. It has to be. It's this custom-built process that guarantees reliability, moving step by step from the smallest component all the way to that final, regulatory sign-off.
So this is way more than just a checklist of tests. It's a whole philosophy on how you achieve certainty in a, frankly, revolutionary product.
That's the absolute key takeaway. The core value here is that testing isn't just a cost. It's the only investment that buys you certainty before you hit start of production. And it's all governed by one ruthless principle.
Fail early, fail cheap.
Fail early, fail cheap. It means that physical prototype testing, the expensive, time-consuming stuff, that's only for final confirmation.
So you should already be, what, 90% sure the truck works before it even touches a real road?
Exactly. If you're discovering a fundamental flaw, whether it's thermal or structural or a logic bug, on a physical B-sample prototype, you've already failed the process. The fix at that stage costs 10, maybe 20 times what it would have in a virtual model.
And that forces the whole engineering team to adopt this strategy they call the shift left mandate.
Yep.
Okay, so let's unpack that. Shift left, it's all about front-loading all that verification work into the digital world, right?
It is. The mandate is to push defect identification as far left on the timeline as possible, away from the expensive physical prototypes. The specific goal here is to catch 80% of all software logic, control, and safety defects while the product is still just a digital blueprint.
80%, that's an ambitious goal.
It's aspirational for sure, but it drives the rigor for everything that follows.
Which brings us to the left side of that classic engineering V model. This is where the virtual development and validation really happens. Let's walk through those three core stages.
Right, the V model gives us our structure. So at the very top, the most abstract level, you have model in the loop, MIL-L.
MIL-L. So this is the concept phase. You're using mathematical models to see if the basic idea even works.
Correct. You're in simulation environments, building a completely abstract model of the whole truck. The engine, the battery, the control logic, everything. The main focus is just validating the fundamental control strategy. How does it manage energy flow between the diesel engine, the electric drive, and that all-important mixer?
And the metric for success here is getting at least 90% logic coverage. But let's dig into that logic for a second, because the mixer truck has really unique priorities.
It does. This is where the hybrid control unit, the HCU, has to make some really tough calls.
Yeah.
In MIL-L, you simulate the absolute extreme scenarios. For instance, the truck is climbing a steep, muddy hill, it needs max torque, the mixer is running, and the battery's state of charge, the SOAPC, just dropped below 20%.
Okay, in a normal passenger hybrid, the brain would probably panic, it would prioritize keeping the car moving, and shut down everything else.
But here, the MIL simulation has to prove the logic does the exact opposite. The risk of canned concrete is greater than the risk of slowing down. So the HCU logic must be proven to prioritize sending power to the ePTO over the wheels.
Even if it means the truck slows to a crawl.
Even if it means the truck's torque gets limited immediately. The mission keeping that drum turning is everything. Proving that core priority is the main job of MILSO.
That really flips the conventional engineering rulebook on its head. So once that high-level logic is proven, you move down to the next level, software in the loop, or SIL.
SIL is where you get real.
Yeah.
You take the actual production-ready embedded C code, the exact ones and zeros that will be on the vehicle's controllers, and you test it in a virtual environment. You're validating the code itself now, not just the concept.
And the coverage goal here jumps up to 95%. Why the higher bar?
Because now we're looking at the actual code paths. You have to make sure every single line of code, especially for fault handling, gets executed and validated. The key task for SIL is diagnostic coverage. You inject virtual faults that would be, impossible or just way too dangerous to do on a real truck.
Give me an example of a critical fault you'd inject during SIL.
Okay, a big one would be a virtual inverter over temperature fault. Let's say the junction temp spikes past 140 degrees Celsius. The software has to see that fault and trigger the correct safe response.
And as we've established, the correct response is not just shutting everything down.
Absolutely not. A sudden power cut on a 32-ton vehicle is a massive safety hazard, especially on a slope. The SIL test has to confirm the production code triggers a smooth controlled degradation, a limp home mode. It gradually reduces torque based on a thermal curve, giving the driver maybe a minute or two to pull over safely. No sudden surprises.
So SIL confirms the code does what Mill promised. Which brings us to the final and maybe most critical virtual stage. Hardware in the loop. Hill.
This is the bridge. This is where the rubber meets the virtual road. You take the real physical controllers, the production HCU, the battery management system, the motor control unit, and you plug them into a real-time simulator.
So you've got the real brains of the truck running a simulated body.
Precisely. And because you're testing the real hardware and software talking to each other, Hill is absolutely essential for ISO 26262 functional safety compliance. The target here is non-negotiable. 100% safety path coverage. Every single failure that could lead to danger has to be tested.
And with high voltage, timing is everything. What's the most critical timing test you run in Hill?
It's all about the high voltage interlock loop.
Right.
The HVIL, that's the low voltage circuit that's constantly checking the integrity of the entire high voltage path. All the cables, the connectors, everything. If that loop gets broken, it means there's a breach. A connector is loose, a solar panel is open.
Which means a potential path for a person to touch 400 volts.
Exactly. The system has to isolate that high voltage instantly and automatically. The Hill test verifies that following an HVIL disconnect signal, the system can open the main contactors and get to a safe, zero potential state in under 200 milliseconds. That's the gold standard.
That whole process, from model to code to hardware, is it's a meticulous roadmap to reduce risk. You're solving 80% of your problems with code, not with a wrench.
That is the whole consultancy mindset, isn't it? Building capability through verification. You don't move forward until the risks are mathematically contained.
Which brings us perfectly to Section 2, navigating the prototype phase gates. Because once you leave the virtual lab, you need a rigid structure. You can't just start, hitting the battery with a hammer before you know the software works.
Correct. You need strict gate management. These prototype stages prevent you from wasting time and money. You have to prove function before you test for durability. Simple as that.
So let's walk through the 4 sample stages and their pass-fail criteria. We start with the mule.
The mule car is your basic feasibility prototype. It's often a Frankenstein's monster, really. An old diesel chassis they've cut up to fit the battery, the P2 motor, the basic cooling system. The only purpose is to see if the core architecture can even exist.
And what's the exit criteria? What does this Frankenstein have to do to pass?
It just has to be stable. The criteria are very clear. No irrecoverable high-voltage faults. So nothing that permanently kills the system. And absolutely 0 instances of uncontrolled torque output. If it doesn't try to run away on its own and the basic switching works, it moves on.
Okay, next up is the A sample, the functional prototype. This one starts to look like a real truck.
It does. With the A sample, we're moving from just feasibility to full functional validation. The focus is now on the mission. Does the ePTO control logic work? Do the charge sustaining strategies actually work in the real world? And you're doing your first physical functional safety tests.
The sign-off criteria must get a lot tougher here.
Oh, significantly. To get out of the A-sample stage, every single test from the functional safety concept has to pass, 100%. And, crucially, you must have 0 remaining Class A software bugs.
Define a Class A bug.
That's a showstopper. A bug that impacts a mission-critical function or safety. If the ePTO fails to start because of a software glitch, that's a Class A bug. Fix it now.
Now we get to the B sample, the structure prototype. This is where the abuse really begins.
This is the big one for durability. The B sample is built with production materials, maybe on pre-production tools. Its entire purpose in life is to expose every structural and durability risk. This is where you execute the full DVP&R vibration, torsion, the environmental extremes, all of it.
And the exit criteria for this one?
Absolute proof of survival. Zero structural cracks anywhere on the chassis or mountings. No measurable degradation of the high-voltage insulation after all the abuse. And a DVP completion rate of 100%. If a B-sample breaks, it means your virtual models are wrong, and that's a very, very expensive step backward.
The exact thing fail early, fail cheap is designed to prevent.
Precisely. And finally, you get to the C-sample, the pilot or PP stage.
This sounds less like engineering and more like preparing for manufacturing.
That's exactly what it is. You're confirming manufacturing consistency. The C-sample is built on the final production line with the final tools. You're just verifying that you can build the truck to spec over and over again without variation.
You mentioned a term CPP index. Let's clarify that.
Right, the exit criteria is a CPEA process capability index of over 1.33. Think of CPK as a score for how well your manufacturing process fits within the engineering tolerances. A CPK of 1.33 is the gold standard. It statistically means you'll have fewer than 3.4 defects per million parts. It's manufacturing's version of functional safety.
It's an incredibly clear pathway. Function, then durability, then repeatability.
And now that we've earned the right to do the tough testing, we need to understand just how tough it gets, because the environment for a cement mixer demands subsystem standards that, frankly, blow passenger cars out of the water.
Okay, let's dive into that subsystem DVP. The extreme engineering, starting with the heart of the system, the high-voltage battery, a mobile fortress.
The battery it's the most critical and the most vulnerable component, and the design priorities are completely flipped on their head. Structural rigidity and thermal safety are prioritized absolutely over energy density. This thing has to survive on a chassis that is constantly vibrating, twisting, and getting hit with shocks.
So if it's designed for that kind of punishment, how do they level up the standard vibration tests?
They start with the SAE J2380 standard, which is the baseline for EV batteries, but then they apply a severely enhanced profile. They especially target the Z-axis, the vertical one, because these heavy trucks just transmit road shocks so much more brutally than a car.
What kind of G-forces are we talking about here?
The test profile mandates a random vibration with an RMS acceleration of at least 8.5 G. To put that in perspective, that's not a single impact. That is a continuous, relentless, high-amplitude pounding that simulates years and years of driving on terrible roads. It's just torture.
And that constant rattling must find weaknesses that a simple bump test would miss.
It leads directly to the most critical part, the resonance dwell test. Engineers put accelerometers all over the pack, and they tweak the vibration frequency from maybe 5 to 200 hertz. They're looking for the natural resonant frequencies of the internal parts, the bus bars, the modules.
And when they find a frequency that makes something resonate,
They dwell on it. They lock the shaker table to that exact frequency and just hammer the battery with it for hours. This simulates the cumulative fatigue of maybe 100,000 kilometers. If a weld breaks or a joint fails here, the design is inadequate. They're not just looking for cracks, they're looking for a drop in insulation resistance that could lead to a short.
Okay, moving from shaking to heat. Thermal runaway is the big fear with any EV battery. What's the goal here?
The baseline regulation, like GB 38031, says you need at least 5 minutes of warning before a fire or explosion after a cell goes into runaway. That gives the driver time to get out.
So 5 minutes is the legal safety net.
It is. But for a high-value asset like this truck, the internal engineering goal is much stricter. No propagation. The design has to ensure that if one cell goes, the event is completely contained within that single module. This means using advanced insulation like aerogel or mica sheets and very specific venting paths to get the hot gas out safely.
No propagation is a huge commitment beyond the minimum standard. Now, let's talk about water. These things get cleaned with pressure washers.
Right. Normal automotive waterproofing, IPX7 or X8, that's for like driving through a puddle.
Yeah.
A mixer truck gets hit with 100-bar water jets at 80 degrees Celsius to get the cement off.
So you need the industrial grade stuff.
You need IP69K certification. The test is intense. They blast the enclosure from multiple angles at close range with high pressure, high temperature water. It has to prove zero ingress. This is absolutely critical for the HV connectors and the battery disconnect unit. Any water gets in there, it's catastrophic.
That's an incredible level of resilience. Okay, let's turn to the mission itself. The electric power takeoff, the ePTO. This is where engineering meets concrete.
This is the soul of the DVPNR. The ePTO failing is a zero-tolerance event. The whole point of the hybrid system is to make sure that drum never, ever stops.
So how do you replicate the absolute worst-case scenario for that motor and gearbox, the moment of maximum strain?
It's a test they call the stall torque test. It's legendary. When concrete sits still for a while, like on a delayed job site, The heavy aggregate settles and the water separates. This creates this incredibly thick, sticky sludge against the drum walls.
It basically becomes a solid mass with huge inertia.
And the torque needed to break that loose can be 3 to 5 times the normal running torque. So the test is, you load the drum with low slump concrete, the thickest stuff, and you let it sit for 1 to 2 hours.
And then you try to start it, just with the electric motor.
That's the moment of truth. The mandate is that the ePTO system must deliver its absolute peak stall torque and hold it for at least 10 seconds without tripping an overcurrent fault or overheating. It proves the whole electric powertrain can handle that initial violent breakaway force.
10 seconds of maximum current. That must be incredible thermal stress on the inverter and the motor windings. What's the backup plan?
The DVP requires validating a multi-layer redundancy. If the electric system can't do it, there has to be a seamless switchover to either the diesel engine for an assist or a completely separate hydraulic backup system. The point is, the mixing continues, no matter what.
And it's not just about starting, it's about the quality of the mix, right?
Exactly. You have to meet standards like ASTM C94. This means the drum's rotational speed has to be stable within plus or minus 1 RPM. It can't fluctuate when the truck accelerates or when the battery so changes. If you lose that precision, the concrete quality is compromised.
All right, finally, the hybrid drive unit, the EDU, that actually moves the truck. It has its own unique thermal challenges.
The big one is low-speed, high-torque operation. Imagine the truck just inching up a steep, muddy ramp. It needs maximum torque, but it's barely moving, so you have almost no airflow for cooling. The motor is generating massive heat with nowhere for it to go.
And you simulate this in the lab with the locked rotor thermal test.
Exactly. You put it on a dyno and command maximum torque at 0 RPM, a complete stall. The cooling system has to prove it can manage that heat load without any component going over its temperature limit.
And if the temperature does start to climb too high, what's the required response?
It has to be a smooth, predictive thermal deaerating. This is critical for safety. The motor control unit calculates the rate of temperature rise and gently starts to limit the current. The key verification is that it's gradual. You can't have an abrupt torque cut that could make a 32-ton truck roll backwards on a hill.
That balancing act again, protecting the hardware while keeping the driver in control. What about mechanical durability for the EDU?
Just as extreme. For the electronics, it's 100 cycles of thermal shock, from minus 40°C to plus 85°C, very quickly. For the gearbox, fatigue testing has to withstand 120% of the rated peak torque, proving it can survive the equivalent of 300,000 kilometers.
And then there's the surprising challenge of electrification noise. When the diesel engine is off, other sounds become really obvious.
The electric motor's high-frequency whine noise. It's usually caused by electromagnetic forces, specifically the 24th and 48th order harmonics. It's in a frequency range that is incredibly annoying to the human ear and causes major driver fatigue over a long shift.
So the fix isn't just more sound deadening material, it's more targeted.
It's acoustic surgery. The DBP&R specifies that the prominence ratio of that whine, how much that specific frequency stands out from the background noise, has to be less than 3 dB inside the cabin. And that requires really fine-tuning the motor control signals and adding specific structural damping.
It's clear the components are built like tanks, but that's not enough. We need to know they work together as a cohesive 32-ton system. Which brings us to Section 4, whole vehicle integration.
This is all about mission reliability and the user experience. Let's start with the power and energy strategy.
The trap here, I'm guessing, is just designing for the standard regulatory test cycles.
That's the disconnect. A standard cycle like the CWTVC, it only simulates driving from the plant to the site. It completely ignores the huge power draw from mixing and especially unloading the concrete.
So if you optimize for the test, the truck could show up for work with a dead battery.
Exactly. The real-world requirement is validating the charge-sustaining strategy. The DVP has to prove that the control system maintains a minimum buffer. The strategy has to guarantee that when the truck arrives on site, the battery associated is still above, say, 30%. That's the non-negotiable reserve needed to finish the job.
And what about just raw heavy-duty performance? It still has to climb.
Oh yeah. At its full 32-ton gross vehicle weight, the truck has to prove it can start from a standstill on a 30% grade and keep climbing for at least 5 minutes. No interruptions, no thermal protection kicking in, just pure sustained power.
Okay, let's talk drivability. P2 hybrids, with the motor between the engine and transmission, can be notoriously jerky.
It's the torque hole problem. When you're switching between EV and hybrid mode, the clutch has to engage or disengage. For a split second, there's a dip in torque delivery. In a heavy truck, the driver feels that as a big jarring hesitation.
That would get old really fast for a driver, so how do you verify that's been eliminated?
You verify the torque fill strategy. The electric motor has to instantly calculate and deliver a little burst of extra torque to perfectly fill that hole during the clutch handover. The key performance indicator is controlling the longitudinal jerk, the rate of change of acceleration.
So what does a low jerk number actually feel like?
Jerk is basically how quickly your head snaps back. The target is to keep it below 5 meters per second cubed. That feels smooth, almost unnoticeable. If it's over 10, it's uncomfortable. Torque fill is the difference between a clunky prototype and a refined production vehicle.
It's amazing how much control is needed just for a smooth ride. Finally, on integration, let's cover acoustic safety, the AVAS system.
Right, in pure electric mode, the truck is silent. That's a huge hazard on a busy construction site. So the Acoustic Vehicle Alerting System, or AVA, is mandatory. The basic requirement is an external sound of over 56 decibels at speeds up to 20 kilometers an hour.
But it's not just about being loud, it has to be informative.
It must be. The critical verification is for the frequency shift functionality. The system has to prove that the pitch of the sound it emits gets higher as the truck speeds up. This lets people around it hear the velocity, just like they would with a normal engine revving up.
We've confirmed the system works as a whole. Now, the final test, the ultimate commitment. Section 5, durability and functional safety.
This is where we prove that 300,000-kilometer promise. We're talking about accelerated life testing, or ALT, compressing a vehicle's entire life into just a few months on a proving ground.
What's the formula for that? How do you compress a decade of use?
The DBPNR is built around the rule that 10,000 kilometers on the proving ground's enhanced surfaces must equal 300,000 kilometers of real customer use. That's a 30-to-1 acceleration factor on average.
And you use specific road surfaces to target specific kinds of failures?
Exactly. You have things like the twist ditch, which is a series of offset bumps that puts maximum torsion on the chassis. That has a 30x factor. But the king is the Belgian block. It's just a nightmare of high-impact, high-frequency shocks. That has a 40x acceleration factor.
So 100 kilometers on Belgian block is like 4,000 kilometers of normal driving. If something is going to break, it'll break there.
And for this hybrid, the focus is really specific. First, the battery pack mounting. You have to ensure the natural resonant frequency of the whole pack and its mounts doesn't overlap with common road frequencies, which are around 15 to 20 hertz. If they do, you get catastrophic resonance.
And the high voltage cables have to survive all that twisting and shaking.
Yes, which leads to the high voltage harness whip test. The orange cables running along the frame get whipped around violently on the twist ditch. You use high-speed cameras to check that the insulation isn't rubbing against the frame and that the mounting clips don't fail.
And beyond just the mechanical abuse, there's the environment itself, the 3 highs, and corrosion.
The truck has to work everywhere. High-temperature testing at plus 45 Celsius while doing a high-power discharge tests the cooling system to its absolute limit. High cold testing at minus 30 Celsius proves the battery can preheat itself and the engine can still start.
And high altitude, what's the specific risk there?
At 3,000 meters or more, the air is thinner. This actually lowers the dielectric strength of the air. For a 400-volt system, this means the physical distance you need between high-voltage components to prevent an arc is greater than at sea level. The DBP has to verify the components are spaced far enough apart to be safe, even in thin air.
What about the unique corrosion risk, cement and acid?
That requires specialized chemical testing following ISO 1675894. The connectors and housings have to survive being coated in alkaline cement slurry, then washed with acidic cleaning agents over and over. You're checking to make sure the seals don't get brittle and the contacts don't corrode.
We've proven it's tough. Now the ultimate safety net. Functional safety, ISO 26262, and the failure matrix.
Functional safety is the promise that the vehicle is controllable even when something breaks. Critical systems like torque control and HV isolation are classified as ASIL C or even ASIL D, the highest level.
And the fault injection test, or FIT matrix, is how you prove that.
It's where you methodically try to break the system. You deliberately inject faults hardware or software and verify the system always fails into a safe, controllable state.
Let's run through a few. The HVIL disconnect again.
That's an ASIL C requirement. You inject the fault and the test is pass-fail. Did the contactors open and torque go to 0 in under 200 milliseconds? If it took 250 milliseconds, you fail. Back to the drawing board.
And an ASIL D failure, what's an example of that?
Regenerative braking over torque. Imagine you're using regen braking on an icy road. If the ABS system detects a wheel locking up, the motor must instantly cut the regenerative torque. If it doesn't, it could lock the rear axle and cause a spin. Verifying that instant cutoff is an ASIL-D requirement.
What about protecting the operator during cleaning?
That's a critical ASIL-C hazard. You have to verify a triple interlock logic. The mixer drum cannot rotate unless three things are true. The parking brake is set, the transmission is in neutral, and the vehicle is in a safe ignition state. The FIT matrix involves trying to override one of those conditions to prove the system still prevents rotation.
It's hardware and software working together to protect the human.
And that commitment extends to always adopting the strictest global standard, mandating IP69K instead of the standard IPX7, or aiming for no propagation on thermal runaway. You build to the highest possible benchmark.
This whole deep dive, it's less a technical manual and more a mission assurance document. It's proof that the vehicle has earned its right to exist by surviving a lifetime of simulated abuse.
That's the essence of the DVP&R. It's the plan that finally allows the engineers to sign their name on the dotted line for mass production.
So, after all that, what does it all mean? Let's summarize the 5 non-negotiable definition of done criteria for that final SOP sign-off.
Okay, the 5 golden rules. First, virtual validation. You must have 100% safety path coverage in hill and 0 Class A software bugs remaining.
Second, battery safety, the foundation of the whole thing.
The pack has to have passed the reinforced SAE J2380 vibration test, including that resonance dwell, and it must have achieved the no propagation goal during a thermal runaway test.
Third, operational capability. Can it do its job?
It must successfully pass the stall torque test for the ePTO. It has to prove it can break loose that settled concrete using its primary or backup power source.
Fourth, vehicle durability, the lifetime promise.
Completion of the full accelerated life test, the 10,000 kilometers on the proving ground, including Belgian block, with absolutely 0 structural failures on the chassis, the battery mounts, or the HV harnesses.
And finally, the ultimate layer of protection.
Functional safety. Every single ISO 26262 fault injection test must be passed. The vehicle has to be proven safe and controllable, even when critical parts fail, meeting all those ASIL-C and D requirements.
For decades, durability in a piece of heavy equipment meant thick steel and a powerful diesel engine. But this deep dive really shows how that definition is changing. Now we're engineering against software bugs, high-frequency whine, and microscopic fatigue that cracks a cable casing.
Right. When you integrate these high-voltage complex electronic systems into these brutal industrial environments, you completely change the risk profile. The biggest threat is no longer just a stripped gear. It's a latent software bug that only shows up under a very specific combination of torque, temperature, and battery charge.
So here's the final thought for you to take away from all this. If a cement mixer operating in this incredibly harsh, corrosive environment with 0 tolerance for failure is now being engineered with this virtual first, shift left strategy and mandatory ISO 26262 safety protocols, how does that change what we should expect from all commercial heavy equipment? From farm equipment to giant mining trucks? What does reliability and safety even mean for them over the next decade?
I think we've just seen the new benchmark for industrial certainty.
Thank you for joining us on the Deep Dive. We'll see you next time.